Okay, so the next one we will look at is the Laplacian. Okay, so this is another matrix, and the definition of this matrix, we'll call this L, and the definition is it's the degree matrix minus the adjacency matrix. Okay? So degree matrix we already saw, it's diagonal with the degrees of the vertices on the diagonal, and the adjacency we saw. Okay? So let's do this for a small example. So the example I want to do is the prism graph, which is one of the graphs in that notebook. So it looks like this. Okay. So this is actually, it's a prism. It's a view of a prism from the top, right? Like a Toblerone. If you look at it from the top, you see the top triangle of the Toblerone and the bottom triangle is big. Okay? It's a prism. And let's now label the vertices. So okay, I labeled it one particular way, so I'm just going to use that. So that's that, and this is 1, 2, and 3. Okay? So that's the prism graph. And then in this case, the Laplacian. So again, the Laplacian is a square matrix. It lives in n by n, or n by n, because both the other matrices are in n by n. And then now to construct this, we first put the degree on the diagonal, okay? So it's D minus A. D is a diagonal matrix. A, remember, has only zeros in the diagonal, so it's not going to mess up the entries from D, okay? So this graph is also regular. It's 3 regular, right? So in the diagonal, you will see 3, 3, 3, 3, 3, 3. Right? There are 6 vertices. That's the D part. And now we have to put minus A into it. Okay? So everybody see that there's no messing with the diagonals. The diagonals don't mess up each other. So for the other bits, you have to remember the label. So if this is like 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Let's just draw one row. So the top row is going to be, I have to look at where the edges are. So vertex 1 is connected to 4 and 2 and 3, okay? So it's connected to 2, it's connected to 3, it's connected to 4, but you have to put a minus because we are subtracting the adjacency matrix, right? And then these two are 0. Everybody okay? And now it's also symmetric. So if you go down, if you have the first row, you also have the first column. So this is also minus 1, minus 1, minus 1, 0, 0. Correct? Did I make a mistake? It's all right? Okay. So then you have to fill up the rest as well. Okay? So this is this matrix. And this matrix is also symmetric. So everything we said about symmetric matrices hold, right? It has real eigenvalues. It has, so you can order them. It has an orthonormal set of eigenvectors. It can be diagonalized. So all of these things come from being symmetric. Okay? So in this case, let's call the eigenvalues, I'm going to call the eigenvalues lambda, and I'm going to order them in the opposite way from the adjacency matrix. So this is the smallest one, and then will come lambda 2 all the way up to lambda n. Okay, so we'll see there's a reason to order it like this. So that's the symbol. So that's that. And then what else? What else do we know about this matrix, this one? It is positive semi-definite, okay? So we'll prove that in a second, that it is positive semi-definite. Positive semi-definite means that the eigenvalues are non-negative. That's one definition. That's the easiest definition to remember, but maybe the hardest definition to work with, okay? So eigenvalues are non-negative is one definition, but there are many other definitions, and we will see at least one more in a short while, okay? So for right now, let's remember that. So we know that this last eigenvalue, whatever it is, it has to be greater or equal to 0, okay? This is coming from the fact, so this is coming from the fact that the Laplacian is positive semi-definite. So positive semi-definite, which by definition means that all eigenvalues are greater or equal to 0. Okay, so that's one definition of positive semi-definite. Okay, so we know that. We'll prove it in a minute. What happens if we do multiply this matrix with the all ones? You get 0? Okay. So if you multiply this with the all ones, you will get 0. You basically get the 0 vector, right? So this is the 0 vector. Does everybody see why? So let's at least try it on this example. So if I multiply this first row with 1, 1, 1, 1, 1, then it'll pick up the 3 edges that are adjacent to 1, right? And then the total from this, and this will be minus 3. But that'll cancel out with the degree of that vertex, which is 3. Okay? So whatever the degree is here will cancel out the rest of the stuff when you multiply with 1, 1, 1, 1, 1. Got it? Does it matter whether it's a regular graph or non-regular graph? This argument. Doesn't matter, okay? So this can be a different degree, doesn't matter, but the degree will cancel out with all the minus ones that correspond to the edges that are coming out of that vertex, okay? So this is always true. It's like this, but we can rewrite this as 0 times the all ones vector, right? This is the same thing. So this tells you that all ones is again an eigenvector with eigenvalue 0, okay? It also tells you that 0 is the first eigenvalue, right? That it's not, so really over here we have equality. So you really have equality here, and this equality comes from this fact, okay? So the first eigenvalue, which has to be non-negative because it's PSD, is actually 0 because of this calculation. This calculation is telling us that, this calculation is telling us that 0 along with the all ones is an eigenpair. Okay? And this has nothing to do with regular graphs. This is true for all graphs. Okay? Regular, non-regular, it's true for all graphs. So unlike adjacency, you have something nicer happening here. It's diagonalizable and so on. So can you work out the relationship between these lambdas and the mu's that we saw before? Okay, so before we had the adjacency matrix, and its eigenvalues were mu1 greater equal to mu2 greater equal to mu n. And now we have the Laplacian, and its eigenvalues are lambda 1, which is 0, less or equal to lambda 2, less or equal to lambda n. Okay? So can you argue how these two are related, for example? So can you see, so let's prove that the mu i's are equal to d minus lambda I for all I. Okay.
For d regular. For d regular.
For d regular, yeah. Okay. Thanks. All right, let's try it. Just try it for a few minutes. Yeah.
The graph is regular, so our degree matrix is actually D into I.
Yeah.
So Di minus A,
yeah.
Since it's the identity matrix, so every eigenvalue will be subtracted by D minus.
Okay, so I think we just got the proof, but maybe everyone try for a minute. What was your name again? Aditi. She just gave us the proof. Yeah.
We will use the characteristics polynomial.
No, it's you can do something very simple. So Aditi's, what was your proof, Aditi? So she's saying that the Laplacian is d times I, this is the degree matrix, minus A, okay? So if I have an eigenvector, say phi, with eigenvalue, I don't know, let's say the eigenvalue is lambda, okay? Then this is equal to di minus A times phi, right? And that's equal to d times phi minus A times phi, right? Okay, so, and this is equal to lambda times phi. Okay? So I took an eigenpair, so what I did is I took an eigenpair lambda phi of the Laplacian. This is the Laplacian, d times the identity minus A, and then we just made a calculation. So because phi is an eigenvector, L phi is lambda phi, right?
If we consider the eigenpair of A, I mean
It's the same.
It's the same. You can switch it. Yeah, it's the same. So this is true, and also this is true. Let's put the other one. So lambda I is equal to d minus mu I. Both are true.
But will it correspond to the same index mu I?
Yes. Yes. Okay. So okay. Should we do it again? It's okay. All right. So so you could make this a little bit nicer. You can call it lambda I phi I, and then play the game. Okay. So here lambda I phi I is equal to L phi I, and this is equal to d minus a phi I. So this is equal to d phi I minus a phi I, like that. And now you have to compare this end with that end. So if you compare those two together, then lambda I minus d goes to the left times phi I is a phi I. Okay? So that means lambda I minus d or d minus lambda I will be one of the eigenvalues of A. Okay? So here, let me write another step. So if this is how this is ordered, then basically I will have this, right? If I put minus everywhere, I will flip the sign on the mu's. Everybody agree? And now if I do d minus mu1, I will still have this d minus mu n. And the claim is that this is exactly this is exactly this, and so on. Okay? So you can go between the eigenvalues of A and L by doing this trick. Okay? If you know one set, you know the other set in a regular graph. Okay? So we're going to use this a lot. So I don't know how a lot, but we're going to use it. Okay? So this is a relationship between the two eigenvalues. Good? Okay. So if you didn't fully get it, you can try it at home. Okay, so now comes my question. Using this fact, can you argue that the largest eigenvalue of the adjacency matrix of a regular graph is D? The largest eigenvalue mu1 of a D regular graph, I claimed, was D. Do you see quickly why this is the case? Let's go the other side. So mu1, or lambda, let's write lambda 1 is d minus mu1. That's what we just proved, right? Lambda 1 is d minus mu1. What do we know about lambda 1? It's 0. It's the first eigenvalue of the Laplacian. So this is 0. So that tells you that mu1 is D. Okay? So this is true for a D regular graph. It's not true otherwise. But for a D regular graph, the largest eigenvalue of the adjacency matrix is D. So D and the all ones was the dominant eigenpair for the A matrix. We don't need any fancy proof. Once you see the Laplacian and you see how they are related, the eigenvalues and eigenvectors, you see immediately that you already know what the top eigenvalue of A was. Okay? For the Laplacian, we know the bottom eigenvalue, which is 0, and it comes with the all ones vector. And for the adjacency matrix, you have the top eigenvalue is D, it comes with the all ones. Okay? So, do you see something else from this proof? So the eigenvalues are related by doing this D minus thingy. What about the eigenvector? They're the same, okay? So lambda I and lambda I and mu I have the same eigenspace, okay? Eigenvalues are different, but the eigenspace is the same because we just used this phi I here, right? This phi I ended up being eigenvector for both lambda I as well as for d minus mu I. Good? So there's no change in the eigenspaces, it's just the eigenvalues get messed up, they change. Good? Okay, so that's the Laplacian. So now let's prove that the Laplacian is PSD. So there are many ways to prove the Laplacian is PSD, arguing that the eigenvalues are non-negative is not so hard, but let's not go that way. We'll use something else, okay? So let me write down definitions of PSD. Okay, so we'll say that a matrix M is PSD, if and only if. So this is a definition. Any one of the following is true. Okay, so the first is that the eigenvalues of M are non-negative. This is one definition. The second definition is that I can write M as some matrix times its transpose. This is a definition, okay? If you can show that, then it's PSD, right? So if this is some n by n matrix, then it could be that this is some n by k and this is k by n. So the B doesn't have to be square. It's just a matrix that multiplies against its transpose to give you back M. Okay, the B is sometimes called a square root of M because it looks like a square root, right? It's like BB transpose is M. So some people call it the square root of M, but it's not necessarily a square matrix. And there are infinitely many possibilities for the square root because in the inside, you can also write this as B times an orthogonal matrix times the transpose of the orthogonal times B transpose, right? This part is the identity if U is an orthogonal matrix. So there's an entire orthogonal group acting on the factorization. So once you have one factorization, you have infinitely many factorizations, okay? So it's not unique. It's like Cholesky, if you know Cholesky, but it doesn't work. Cholesky doesn't work for things that have zero determinant, but this you can do, okay? So this is a second definition. This is what we're going to show now, that the Laplacian has this property. And then another property is that if you take the quadratic form, so this x is vector of x, so this means x1 through xn times L times x1 through xn. This is the quadratic form of the matrix. So this is non-negative for all x. Okay, that's another definition of PSD. And there's a fourth definition. Does anybody know it? It's not important, but for us, it's very important for other purposes. All the principal minors are non-negative, okay? But I don't think we'll use it at all in this course, but there is another definition using principal minors. Okay, so let's not worry about it. So I want to use this. I want to argue that the Laplacian is PSD by showing that you can factor it, okay? And this we will use a lot, so let's try to understand. So I'm going to start this exercise. We're going to prove that it's PSD. I'm going to show you what to do, and then you can check that it works, okay? So let's prove, so the theorem, or whatever you want to call it, or exercise, is that L is PSD. By the way, the notation for this is this. Okay, so you do this curly grade A equal to 0. In tech, you write this as, you know this? Okay, that's the tech command for this curly grade A equal to 0. Okay, it's called the Lohner order, and it's in that ordering. This is like a non-negative vector. That's essentially how this works. Okay, anyway, this is just notation. It's just notation. We're going to show that it's PSD by showing this part 2, that it factors, okay? All right, so what do we do? So here's the recipe. So I'm going to define B to be a directed node edge matrix of the graph, okay? So this is the only time in this class that you will see a directed graph. But let's do it on an example. It's easier to explain on an example. Okay, so suppose I have a graph like this, 1, 2, 4, and 3. Okay, so undirected graph. So all our graphs are undirected. So a directed node edge matrix means first you pick an arbitrary direction on the edges, any, okay? So I'm going to direct this lexicographically. So let's send 1 to 2, so smaller number to bigger number, 1 to 4, 2 to 3, 2 to 4, and 3 to 4. Okay, this is an arbitrary direction. I just put some direction. And now we're going to construct this matrix B to be a matrix that has the nodes on the rows and the edges on the columns. Okay? So this will have nodes are going to be 1, 2, 3, and 4. These are the vertices of the graph. And on the columns, you put all the edges. So the edges are 1, 2, then there is 1, 4. Let's do everything that's connected to 1. And then there's 2, 3, there's 2, 4, and there is 3, 4. Okay? So this is not a square matrix anymore. It's got maybe many edges, few vertices, I don't know, some rectangular matrix. And then the rule is that we're going to take each of these arrows. So if I go to the 1, 4 entry, I'm going to put a -1 where you see a 1 and +1 where you see a 4. Okay? So let's do it. We'll do it on an example, then I'll write the formula. So for 1, 2, this is this edge. Okay? So I go to the two nodes 1 and 2, and I put a 1 for the tail and a -1 for the head. Does that make sense? So this is the column of edge 1, 2. 1, 2 involves only two vertices, 1 and 2. Okay? In row 1, which is the tail of the arrow, you put 1. And in the head, you put a -1 in that column. Nothing else in that column. Because the column only involves two vertices, right? Corresponding to the single edge, right? Rest are zeros, yeah. So you put a -1 and then 0 and 0. Okay, let's do a few more. This is a little confusing. So what happens in 1, 4? So in position, doesn't matter. Okay, so you can either make the tails -1 and the heads 1, but you have to stick to whatever you pick. Don't mess it up. Like, it's not a random thing. Don't change the rule in the middle of the game. Okay, so pick what you want. So pick how you direct. Pick whether tails are 1s or -1s. Heads are the other thing. Okay, so let's do 1, 4. What happens? So 1, 4, I did it lexicographically so it's easy to remember. So 1 is smaller than 4, so this is always the tail. And 4 is the head, so you put a -1, and the rest are zeros. Is that okay? This is this matrix. This is called the directed node edge incidence matrix. Make sense? It's nodes incidence matrix, yeah. Yeah. Okay, everybody okay with this? Okay, so this is this matrix B. And so the rule was that in position ij, we put a 1 if I is, oh no, it's not position ij. Okay, can I just avoid writing this? You understood it, right? So it's kij, right? Because k is the row index, this is the vertex, this is the edge, this is the column index, okay? So every entry of the B matrix has a vertex as the first index and an edge as the second index. So it's kij, okay? And the rule is, in this thing is going to be 1 if I is k, okay? It's going to be -1 if j is k, and it's going to be 0 otherwise. Okay, so that's a rule. All right, so can you check on this example that if you do BB transpose, you get the Laplacian? Please check. Just check on this example. So you have to finish the matrix first. At least check a bit of the Laplacian, maybe not everything. So I'll write the Laplacian here. Laplacian of the undirected version of this graph. That's what I mean, okay? So. Two plus 3, 4. 3 is 2, 2, 2, 4, and 4 is 3. Okay, that's the Laplacian. So please check that if you did BB transpose, let's also write this. 2, 3. Just check one row at least. See if it works out. Okay, so you can finish the calculation, but this is the true. So this is really, and you can try to prove this in general. Okay, I just did this on an example, but this is one way to prove that the Laplacian is PSD. Okay, so you argue that it is equal to BB transpose, where B is a directed node edge incidence matrix. Okay, great. So if you have this, then can you tell me what happens to the quadratic form? So quadratic form was one of the definitions, right? So let's look at L transpose LX. This is a quadratic form of, every symmetric matrix has a quadratic form. You can write, this means, what does this mean? So this means that in our example, it means I take x1, x2, x3, x4. These are variables. And then you put the Laplacian here. And then you multiply on the other side with the same vector. But so you write this is the transpose. This is the real vector. This is the Laplacian. Okay? So when you finish multiplying this, you will get a quadratic function in the x's. Do you agree? Because x's are not numbers, they're variables. So when I finish multiplying, these x's will multiply against those x's and give you something quadratic, right? It's called the quadratic form. And can we see what that is for a Laplacian? So in our example, so this should be in general what? So if I have x transpose LX, let's write L as BB transpose. We know there is some B, right, that does this, and it's this, okay? Now do you see what that is? Okay, so lots of things are happening here, right? So one thing that's happening is that here I have x1 through xn, and then it's multiplying against the B, this is the B. And then here I have B transpose. Okay, so first of all, before we even do that, before we do this big expanded form, do you see this is non-negative? So what is this, right? This part and this part, how are they related? They're transposes, exactly. So this is really B transpose X norm square. Do you agree? So it's B transpose X times its transpose. So it's something, that's what that is. So this is non-negative, okay? So if you can factor like that, then the quadratic form is non-negative. Quadratic form is non-negative is a definition of PSD. So this is one direction of a proof that tells you if you have property 2, then you have property 3, okay? So it's non-negative. But in our example, let's see what this is, right? So let's actually look at just one piece. Let's look at X transpose B. Okay, let's look at one piece. So this is going to be in our example x1, x2, x3, x4. And then here is the B, which is something rectangular. So I need a little bit more space. And this one in our example is 1 minus 1, 0, 0. And then 0, 1, 0, 0, minus 1. And 0, 1, minus 1, 0. And 0, 1, 0, minus 1, 0, 0, 1, minus 1. Okay, this is what it is, okay? So when you do this, first of all, you'll get a row vector. Do you agree? It's going to be a row vector. What happens when you multiply this against this? What do you pick up? Just louder, please.
xi minus xj.
X, that's right. Exactly. So this multiplication is going to give me x1 minus x2. But this is the edge that corresponds to 1, 2, right? So from there, I'm going to get x1 minus x2. And then the next one is going to be x1 minus x4. And that corresponded to this edge, 1, 4. And in general, I'm just going to pick up all the edges. But it's going to be written as a linear form, where the first variable is the first vertex and the second variable is the second vertex, okay? So if I finish this, so in general, this is going to be a vector whose ij entry is xi minus xj, where this is the entry that corresponds to the edge ij, right? This is what this is going to be. Everybody okay with this? So we can finish this if you like, but this is x1 minus x4, then I have x2 minus x3, and then I have x2 minus x4. Exactly, right? So we basically get a vector where every entry corresponds to an edge, and the edge is recorded as xi minus xj. Do you agree? What happens now if we take the norm square of that thing? That's what this is, right? So we just computed this first piece, and this is the transpose of it. So I just computed the first piece, it came out to be this row vector. And now if I compute the other piece, it's going to be the same vector, but a column vector. Then when I multiply the two, I get the norm square. So what's our general expression here? Can we write one? So all of them will look like xi minus xj square, right? Sum over all the edges. Is this okay? So this is the quadratic form that comes from the Laplacian. And this is going to be very, very important for us, this quadratic form. Everybody okay? So it has this nice interpretation in terms of the graph, that it's really that, and that also shows you immediately it's non-negative, right? It's a non-negative polynomial. What else about it? Do you know more about it? Like what kind of function is it? It's a quadratic function whose domain is the number of vertices, right? Like x1 through x4 is the Rn is the domain. Do you know something more about these kinds of quadratic forms or these? If the matrix is PSD, so it's non-negative, so its graph, I can't draw this in 4 variables, but the graph has to be above the domain. This is the domain, okay, this is Rn. So it's non-negative, it's above the domain, but it's also convex, okay? Convex means that if you pour soup in, it doesn't fall out. That's the definition of convex, okay? So it really is, you know, convex, right? From calculus, yeah. So that's convex. So it's actually a convex non-negative function, which is very special. You can have lots of non-negative functions. Like for example, this is a non-negative function on the reals, but it's not convex. But if you have this, it's convex, okay? So anytime you have a PSD matrix, the quadratic form will be non-negative and convex, if and only if. Okay, so it's a pretty strong type of quadratic form that comes out of the Laplacian. Okay, so that's the Laplacian. Right. So now let's actually use this quadratic form. Was there a question? Everybody okay with this argument? Did you have a question? Feel free to ask. I'm going to switch gears for a minute and do something else.
Can you repeat that? If the matrix is PSD, then
if the matrix is PSD, the symmetric matrix, the quadratic form is always non-negative and convex. Yeah. Non-negative is the definition of PSD in a way, but convexity is a little bit more. Okay? So I don't know if you saw my notes, there are some pictures in the notes. Like if you take just some arbitrary symmetric matrix like the adjacency matrix and make its quadratic form, it won't be non-negative. It won't be, you know, and it won't be convex either. But when you pass to the Laplacian, it becomes this sort of bowl-like thing. Okay? So it becomes non-negative and convex. Okay, so now let's actually use this quadratic form to understand the eigenvalues a little bit better. So this is important, okay? That this is the quadratic form that comes from the Laplacian. And we got it for free from that factorization of the Laplacian. You can also prove this from scratch without that factorization. You can just look at how the Laplacian is written and then you'll get this, okay? So if you want, you can try it without the BB transpose. But the BB, I mean, these are just ways to illustrate the different definitions. Okay, so now let's actually prove the, when do we stop? Okay, plenty of time. Okay, I'm going to prove Courant-Fischer in a short bit, okay? It's a very, it's maybe the most longest proof for today, but we'll do that. But before that, I want to actually introduce because we'll need it for other things. So I want to make sure that everybody knows that theorem very well. Okay, so let's write down a definition. So the Rayleigh quotient of X with respect to L. So again, I'm only doing everything in the context of these graph matrices. All of these things are more general. They hold for all symmetric matrices and so on, okay? So either you know that or you don't know that, but don't worry. We're just doing this for these graph matrices. Okay, so it's written like this, RLX. And this is basically the quadratic form divided by X transpose X. Okay, so rational function. Top is a quadratic, bottom is also quadratic, and that's the definition. That's the definition, okay? So what is it? Can you think what this is? So the quadratic form is this like bowl-like thing, right? If I draw a picture of it on the domain, I will get a bowl. If I divide by X transpose X, then do you see what's happening? What is happening to that quadratic form? Or where are we evaluating it? Only on the unit sphere, okay? So this is just saying that whatever X I use, just normalize it down to a unit vector, right? So here is the sphere, here's the origin, and you may have a vector, so this may be your X, okay? And the X has this top part, X transpose LX. But now if I take the value of X transpose LX at this X and divide by the norm square of X, you're essentially calculating the value here, okay? So you're just evaluating on the unit sphere. So the domain is now cut down to the unit sphere, and you're just calculating the value of the quadratic form. Good? It's essentially the quadratic form. We've just normalized it, that's all, okay? But it's going to be useful to normalize it. So this is the Rayleigh quotient. And let's check, so okay, from what we just saw, this is sum of xi minus xj, the whole square, over all ij's that are edges, divided by the norm of x square, right? X transpose x is the same as norm of x square. So that is what that is. Okay, so can you evaluate this Rayleigh quotient on an eigenpair? So let's take an eigenpair. So check that if I have an eigenpair lambda phi, okay, this is now eigenpair of the Laplacian, okay? Can you see what happens if you plug in R phi L? So just have a look. Okay, so in the place of x, you plug in the eigenvector. See what happens. So this by definition should be phi transpose L phi divided by the norm of phi square. Okay? Instead of x, I'm using phi. Phi is a vector, right? So I can use that.
RL.
But I changed the notation, yeah, so sorry. L phi. Indeed. So what happens? Something nice happens, right? So this L phi is, yeah, so L phi is lambda phi divided by the norm of phi square. But lambda is a number, so I can take it out. It's a scalar. So in the top, I get phi transpose phi divided by, again, phi transpose phi, right? So these will cancel because phi is not the zero vector ever. So the denominator is okay, this is well defined. So this just ends up being lambda. Okay, so this is a very nice fact that if you take the Rayleigh quotient and you evaluate it on an eigenvector, you just get lambda back, the eigenvalue of that eigenvector. Okay, so in fact, if you take an entire eigenspace of an eigenvalue, the Rayleigh quotient has the same value. It just has the value of the lambda. Okay. So, of course, why do we study eigenvalues, eigenvectors, right? They tell you information about the operator. The matrix is an operator, it's a linear transformation. We want to understand where is it fixed. That's why we study eigenvalues, eigenvectors. And the other big thing to study is singular values, singular vectors. And those tell you what the matrix does to a sphere, basically. It also allows us to reduce the action of any linear transformation to the action of a diagonal matrix by basis change. Okay? So this is a big reason why we study these two guys. Eigenvalues, eigenvectors, or singular values, singular vectors. They give you tons of information about the operator. So singular values, singular vectors, of course, even more fancy than eigenvalue, eigenvector. So it's somehow a secret to mathematicians, I find, in the US. Nobody teaches singular values, singular vectors in a math department. You should revolt against that. It's really important, okay? It tells you a lot about the structure of the operator. Okay, so everybody good with this? Okay, so this is saying this, okay? So that RL phi is lambda. Okay, so now let's do one more thing, right? So this is saying, so suppose for a moment, let's just make things simple. Let's assume that our eigenvector is unit norm, okay? So we will often use this. We can, right? Why not? So let's assume that it's our unit norm. So then the Rayleigh or X trans or phi transpose L phi is just the eigenvalue, right? Because the bottom is just 1. So this is just the eigenvalue. And this, on the other hand, is this, right? So this implies that if you take the sum of phi I minus phi j square over all edges, you get the eigenvalue, right? Because I just use the fact that this quadratic form is this for the Laplacian, all right? Now this is actually telling you something super interesting. So let's take a look at this, okay? This part. So what happens if lambda is really small, like close to 0? Not 0, but close to 0, okay? Very small. How big can these things be, these differences? They have to be very close together, right? They have to be very, very small. So that means your eigenvector is varying very slightly as you move from one vertex to the next vertex. So it's like a smooth function, okay? So small eigenvalue means the variation of the eigenvectors as you move along the graph is very, very slight. Big eigenvalue means there's big oscillations. So I'll show you a picture in a second, but there's going to be big oscillations. You have big difference across the edges, okay? So this is just across one edge, right? So if you have a small eigenvalue, when you go from here to here, the difference better be really small, because these are all positive things when you square them, and they're adding up to give you lambda. So if lambda is small, these squares have to be small. That means the differences are really small. That means phi is really smooth. Okay? So this is like doing Fourier analysis. So when you have small eigenvalues, the eigenvectors vary very smoothly across the graph. When you have high eigenvalues, they oscillate rapidly. So like when you do Fourier analysis, we have the cosine sine basis, right? So if you do sine theta, cosine theta, it's nice. If you do sine 100 theta, cosine 100 theta, it's oscillating widely. Those are the high eigenvalues and the eigenvectors, okay? So there is a notion of, so you can sort of understand functions of graphs in terms of, like if you have some crazy function on a graph, like we take everybody in this class and we calculate their, I don't know, cholesterol level, okay? That's what we old people do, calculate cholesterol. So if we do that, and say you're related somehow, like you're from the same institution, or you're of the same age, like there's a graph on this class, then if we look at we make a graph, we compute its eigenvalues and eigenvectors. The small eigenvalues are going to correspond to so it could be that the cholesterol variation is quite smooth in this class because all of you are roughly the same age, roughly the same, everything, right? Ethnicity, everything. So your cholesterol function is going to go smoothly over the graph of this class, okay? That means your cholesterol function is a combination of very low eigenvectors that come from low eigenvalues. You don't need this wildly oscillating thing, right? But if you went to New York City and did the same thing, you probably need those high eigenvectors, right? So it's really nice to understand the connection here. Okay, so let's see a picture first, and so that we can just take a short picture break, and then we'll come back to Courant-Fischer. Okay. Came up. Yeah, so this was it. So down on line 325, there is this graph called the Thomason graph. It's just one of the graphs in Mathematica, okay? So I pulled it up, and then I calculated, so it's called G. I calculated its Laplacian matrix. So in Mathematica, it's called the Kirchhoff matrix. So it's not called the Laplacian, okay? So you pull up the Laplacian, so that's that. And then I'm looking at the eigenvectors of the Laplacian, but I just look at the second last one. So, okay, maybe we should before I do this, let's go back and look at how eigenvectors of the Laplacian come out.
Peterson.
Yeah, here's Peterson. Okay, so that's the Laplacian of the Peterson. Everybody agree? There's 3, 3, 3, 3 on the diagonal and -1s in other places where there are edges. Eigenvalues are here. 0 is the smallest, then it goes up. Okay? So in Mathematica, it always gives you the biggest and then goes to the last, the smallest. Now there's no absolute value because it's the same, right? Everything is non-negative. These are the eigenvectors, and then same for some other graphs, maybe not so important right now. But let's look at, yeah, so the key thing I wanted you to note.
The last time.
Second one.
Yeah, the key thing I want you to note is that I'm taking the second last eigenvector, which means small eigenvalue, right? Because 0 is the last eigenvalue in Mathematica. So that would be the -1 eigenvalue, and the corresponding eigenvector would be the -1 eigenvector. Yeah, it's a small, so I'm taking a very small eigenvalue, okay, of the Thomason graph. That's this -2. And then there's some normalization going on here, not so important. And then I'm asking it to color it. So the colors tell you the values of the coordinates of the eigenvector, okay? So this eigenvector has plus and minus in it. It doesn't matter, it probably does. But you see, as you go from, I don't know if you can see this well. You can probably see it better in your laptop. But as we walk from one end of the graph to the other, you see the colors are moving very smoothly, right? You don't have these big jumps, like red doesn't immediately go to blue. It's just variations on red, and then it slowly becomes blue. Is that okay? All right, let's see if this will work. I'm going to try a different eigenvector. So it's the Thomason graph. So let's change this. So this has a lot of vertices. Let's take the 30th eigenvector, for example. Or I can take the top. Let's take the 4th eigenvector from the top. Okay, now look at it. I don't know if you can see. It's completely jumbled up, right? So that means there are big variations when you jump from across edges. So these are like the high frequency vectors in a Fourier basis, okay? So eigenvectors have this physics connotation to it. Low eigenvalue, smooth eigenvectors. High eigenvalue, highly oscillatory eigenvectors. So that means if you want to model a smooth function, you probably don't need those high parts of the spectrum. Okay? So this is a very nice thing that comes out of what we just studied. Yeah?
So I didn't understand what was that -2 and 4, right?
Oh, so this is the position of the eigenvector. So this 4 means I'm taking the 4th eigenvector in my mathematical list. So it corresponds to the 4th largest eigenvalue. Okay?
And the eigenvector corresponding to that.
Yes. So if I write -1, then it's the last eigenvalue, which we know is 0. So that's why I did -2, which is the second last eigenvalue, which is really small.
But why is -1 the last? Because the eigenvalue is -1.
No, it's
No, the index. It's the index.
it's a Mathematica notation. Okay?
Indexing from the right.
Yeah. So exactly. So the eigenvectors are phi1, phi2 up to phi whatever, phi n. This is for the Laplacian, this is the smallest. So in Mathematica, this is indexed 1. This is indexed 2, and so on. This is the first from the back. So it's indexed -1. It's syntax.
You could have
That's
put
all.
n also. It doesn't, but you'd have to know what n is.
Yeah, exactly. You have to know.
And then
You
it's
just
easier
put
to say.
minus.
Yeah. Make sense? So again, please play with this at home. You can see this variation. This graph has a lot of vertices, so you can see this variation. Okay, good. So that was an important observation. Any more questions on this? Everybody got this? Okay, you can play with other ones. We can spend a lot of time playing. I don't want to do that. So let's move on to Courant-Fischer. And then if we have time, we can come back and do more. Okay, so for tomorrow, this is going to be really important. The fact that when I say low eigenvectors, I mean those corresponding to low eigenvalues, okay? Those are enough to model smooth functions, like your cholesterol function. And we rarely need the high frequency. So this is, yeah?
See, we have actually taken now low eigenvalues and we have shown some continuity, smoothness is there,
Yeah.
visibility wise.
Yeah.
But it is defined by the ratio or the difference you take between the
Edges,
numbers.
yeah.
So is there any formal name for that thing, whatever you have taken?
So this is, this is not like a hard and fast theorem. It's like a heuristic, right? Like if you had a bipartite graph, which means you have vertices on this side, vertices on the other side, edges only go between, then you'll see that the eigenvectors and eigenvalues actually jump a lot, okay? So it's kind of a heuristic, it's kind of a feeling, if you like, right? It's true for most graphs, this what I just said. And we saw the reason, right? The reason is really, I don't know if there's a name for that difference, if that's what you're asking. I don't know.
See, it's all basically boils down to the value which you are choosing, how we represent. We can actually choose a value so that that smoothness disappears when you go very granular level. So that particular, I'm not getting what is that actual defining value.
So I guess all I'm trying to say is that, all I'm trying to say is that because if you plug in an eigenvector into the quadratic form, you get lambda, okay, that we checked. But this is also this, okay? So if your lambda is small, the other side has to be small. But the other side is the sum of positive things. That means each piece has to be small. So that means the phi I and the phi j across an edge ij must be close. That's it.
There's no, this is a discrete thing, no? So you can't talk about smoothness as a function.
Sir, for visualization purpose, we have chosen a value here, which actually showed us this kind of smoothness.
What value are you worrying about?
That's what I am asking, sir. What is that which made us to visualize it for lower eigenvalues, smoothness, or high eigenvalues, with randomness appearance wise? What is that in the code which actually made it?
So we're choosing, in this example, I chose the fourth eigenvector of this graph.
Yeah, ma'am, but what is that visualization which made us actually visualize this way?
What is the actual visualization?
Yeah, in the visualization, which is the actual value which made us to see?
Let's talk about that later. So there's some normalization and so on going on, and then mapping of numbers to colors. There's, so it's like a heat map, right? Like if you see a heat map, this is how it looks.
I think he's looking for a solution like a least square approximation.
Oh.
Somewhere over there, like we have kind of a least square, but it's not the vectors. It's completely different.
Yeah, it's just.
In the syntax that is giving you this.
Yeah, so.
The RGB colors.
Yeah, so there's a mapping that's happening. Okay, these two lines of code are a little bit complex, but we can talk about that offline, okay? So all we're doing is, if you just took the numbers and put it here, you'd get the same picture. It just wouldn't be so nice. So we've just normalized the values, yeah.
Did you say that Kirchhoff matrix is the same as the Laplacian?
Laplacian, correct. So in Mathematica, there's no Laplacian command. It's called Kirchhoff matrix, okay? So you want to call the Kirchhoff matrix.
If we want to find the Laplacian of every matrix, we say Kirchhoff.
Exactly. So like in this, so I don't know, maybe Peterson. So I asked so I'm giving the name L Peterson graph for the Laplacian, and the command is Kirchhoff matrix Peterson graph. Okay, that's just the name inside Mathematica. I mean, all these things have physics meanings. That's why they're called like that. So Kirchhoff's laws, electricity, whatever. Okay, that's it. All right, I will come back to it in the break, okay? But hopefully you got the gist of it, right? Small eigenvalue, smooth eigenvector. Okay, so let's do Courant-Fischer. Okay, so this is a really, really important theorem. It says that lambda k, so I'm only talking about the Laplacian. So lambda k is the max of the min of the quadratic form divided by x transpose x. This is the Rayleigh quotient, okay? So it's the min over all x's in S that are not zero. What is S? S is all subspaces in Rn, subspace, and the dimension of S is n plus 1 minus k. Okay? This is one piece of the Courant-Fischer theorem. There's another piece that switches the max and the min, but let's just do this one piece today. Okay? So every eigenvalue, this is true for all symmetric matrices, not just for Laplacian, okay? So if I take the Rayleigh quotient and calculate, what am I doing, right? We are, yeah, do you have a question? The kth eigenvalue. The kth eigenvalue, okay? So the kth eigenvalue of the Laplacian is calculated like this. So let's just parse what this is saying. This is the Rayleigh quotient. You take the minimum of the Rayleigh quotient over all non-zero vectors in S, and you vary that, and S is a subspace of this dimension. So you take the minimum over S, and then over all S's you take the maximum. Okay? So pick an S, subspace of dimension n plus 1 minus k, calculate the minimum of the Rayleigh quotient, and then do this for all S's of that dimension, and pick the maximum of this minimum. All right? So these are called variational characterizations of eigenvalues. It's very analytic. It's very, very useful. Have you seen this before? Some people, maybe? Okay, let's prove it, okay? So I want to prove this and then we'll break for lunch. Okay, so there's another piece which I'm not writing here right now. So let's do proof. Okay? So we can actually shut this down if you want. It'll just cut the feed, right? Can I just make this go up, Arvind? Oh. Okay, so we'll start the proof here. So I'm going to first pick S to be the span of phi k up to phi n. Okay, so these are the so remember the eigenvalues are lambda 1, which is 0, then lambda 2, all the way here is lambda k, and this lambda n. Okay, and they go with eigenvectors phi 1, phi 2, phi k, phi n. This is the Laplacian story, right? So I'm taking the span of the top n minus k plus 1 eigenvectors. So I'm starting from here and taking all of these guys, okay? That is S. So the dimension, so remember these eigenvectors they form a basis of space, they are independent. So if I pick a subset of them, still independent. Do you see that the dimension is n plus 1 minus k? Okay, so check it. This is like n minus 0. This is n minus k. So it's that, okay? So check that. So that's the number of eigenvectors in that list. So that's the dimension of the space. Okay, good. So we take that one. So that's one of these S's, right? I want to take, for every S, I need to calculate the minimum and then take the maximum. I'm picking a particular S, this S, okay? Right. So let's see what happens if I pick an X in S, okay? I have to calculate the minimum over all X's in S, this bit, right? So let's pick an X in S. So this implies that X is a linear combination, so it's equal to Ci phi I, where I goes from 1 to k, k to n. Do you agree? So if I pick an X in S, it looks like that. It's a linear combination. So then I can calculate X transpose Lx, right? Let's calculate this. So X transpose LX is going to be the sum of Ci phi, but now I have to take the transpose and sum. This goes from K to N, and then I have L, and then I have sum of Ci phi. I goes from K to N, and without the transpose. Okay? So I picked an X in my subspace, which I fixed, and then I'm just calculating what the quadratic form looks like. So, sorry? Oh, Cj, Fj, yeah, let's change the index, that's a good idea. So let's change the index, and now J goes from K to N, okay? Good, so now do you see what's happening? So this L, I can bring and stick it next to this phi, right? And then L phi I is lambda I phi I. So that allows me to get rid of a little bit, okay? So this becomes equal to sum of Ci phi I transpose. The first part is still there, let me not worry about the indices. The next part is going to be sum Cj, and then L phi j, and j goes from 1 to n, right? L phi j, okay? And now L phi j is the same thing as lambda j phi j. So I can replace L phi j with lambda j phi j, right? Because it's an eigenvector with an eigenvalue. Good? Okay, so then this calculation, let's take it over here. So what we have so far is that X transpose Lx is equal to that thing over there. And that thing over there is going to be sum of Ci phi I from K to N. And then here sum Cj, lambda j, phi j from K to N. Did I get it? Transpose, yeah, correct. Okay. Okay, so lambda j, so what is this? So this is some big sum, right? So it's some big sum, and what will survive? The phi i's and the phi j's are orthogonal to each other. So they're going to cancel out and give you 0 unless phi I and phi j are the same index, right? Phi I will be okay, but phi I, phi j, where I and j are different, won't give you anything, okay? So do you see what's going to happen? This will be, yeah, so maybe we won't skip a step. So let's write this as Ci Cj, lambda j, phi I transpose phi j. Okay, this is just the blind one. Okay, I just made the calculation. And then I'm going to be able to get rid of everything where I and j have different indices. Okay, so this is going to be sum of Ci square from K to N. Okay, and then what happens? It's really phi transpose that survives, right?
Phi transpose.
No, phi, what survives?
Phi transpose phi is 1.
Yeah, phi transpose phi is 1. So lambda I will survive. And then phi transpose phi is 1. Okay, so I don't need to write that. Do you see? Does everybody see that? Phi transpose will survive. But this is just the norm of phi, which we can assume is 1. Okay? So this is just equal to sum of Ci square lambda I from K to N. So far. Everybody okay? Okay. Now remember, lambda k is the smallest of all these eigenvalues that we are considering here, right? So this means that this is, whatever the sum is, this is greater equal to lambda k times sum of Ci square, K to N. Do you agree? Because lambda k is the smallest eigenvalue. So if I replaced, so this is lambda, goes from lambda k plus 1 up to lambda n. So if I just stuck in lambda k for all the lambda i's, I will get this, and that's definitely smaller because these things are all positive, right? I mean, everything is positive in this example. So I get that, okay? So I get that. Now, on the other hand, what is X transpose X? Let's also look at that, okay? So X was this. Do you see what that'll come out to? So this is sum of Ci phi transpose times sum of Cj phi j transpose. No transpose, correct? Okay. So this, what is this? Ci square. So the only thing that will survive is this. Okay? So then what happens to our Rayleigh quotient? So we have this first piece, and then we have this second piece. Okay, this is the first piece, this is the second piece. So this implies that if you take the Rayleigh quotient, this is greater equal to lambda k. Do you agree? Okay. So for this particular subspace, we saw that the Rayleigh quotient is greater equal to lambda k. Does it achieve lambda k on this subspace?
When x is 5k.
Exactly. When x is 5k, we just saw that it does achieve it, right? So actually the whatever this is, the minimum is greater equal to lambda k, but it also is lambda k, the minimum, right? This is like a great trick, right? If you have this greater equal to this, I can put minimum here is going to be greater equal to minimum here, but minimum, this is just a number, so there's no minimum. So this implies that the min of the Rayleigh quotient, or let's just write it like this, x transpose Lx, x transpose x over all x and s not equal to 0 is greater equal to lambda k, but it's actually equal to lambda k because the minimum is achieved by phi k, right? So we have this one subspace, very special one that we picked, where the minimum is lambda k. Okay, good, okay. So that in this business over here, I picked one subspace and argued that the minimum is lambda k, okay? Now I'm going to argue that if you pick any other subspace of the same dimension, the minimum is going to be smaller than lambda k, smaller equal. That means the max of the mins has to be lambda k, right? So I'm going to pick another subspace of the same dimension in 6 minutes. So let us see if we can achieve this. All right, everybody good so far? Okay. So let's keep going that way. It's like Hebrew. So, what?
Urdu in English.
Urdu, okay, Urdu. Yeah, okay. I didn't know Urdu was written like that. All right, so now there's this lovely trick that's going to finish the proof, okay? All right, so now let's suppose S prime is any subspace. Of dimension n plus 1 minus k, okay? So I have to now vary over any subspace and argue that the Rayleigh quotient is going to be no more than lambda k, right? Max of the min has to be lambda k. I already got one with lambda k, so everything else better be less or equal, okay? Good, okay, so this is something like there. And now let's also let T be the span of the first k eigenvectors, phi1, phi2, up to phi k, okay? So that means in this picture over here, we are taking these guys from here to here, okay? That's T. So I'm taking the span of the first k. And S prime is just some arbitrary thing of dimension n plus 1 minus k, okay? Will those two subspaces intersect non-trivially? Yes, right? Because they overlap, like the dimension doesn't add up to n, so they have to have something in it that's not 0, okay? So if I want to calculate the min, so the key observation is T intersect S prime is not just 0. It has to have something more. Any two subspaces will of course intersect in 0, but this has something more, okay? Something non-zero in it. Okay, so let's calculate the minimum over x and S prime, not 0, of the Rayleigh quotient. So I'm trying to argue that this cannot exceed lambda k, right? I'm varying now over an arbitrary subspace, and I want to say the minimum is less or equal to lambda k. Therefore, when you take the max over all of these guys, you still have lambda k, okay? All right, so we take this. And this is definitely less than the minimum over all x in the intersection of S prime and T of this. Do you agree with this? So S prime is a subspace. If I only look in a piece of it, which is S prime intersect T, the minimum will not be as good as the overall minimum, okay? So this minimum is definitely less than this minimum where I have restricted the domain to be a part of the original domain, okay? Good? All right, now comes the nice thing. This min is less or equal to the max of x transpose Lx over x transpose x over all x in T. Drop the S prime. Okay, is it computing? Yes? Okay, so we had S, we were looking at S prime, we were looking at the minimum. That minimum is less or equal to the minimum if you restrict S prime. But now this minimum, whatever this is, it's part T is in here. So if I take this number, the minimum value of this on T, that has to be less or equal to the max on all of T. Right? T has, we switch from max to min to max. Okay, so that's that. So we have all this. So now we again calculate what happens if x is in T. Okay, so let's deal with that last piece. So if x is in T, then x is equal to sum of Ci phi. I goes from 1 to k this time, right? And we do the same calculation. I'm going to calculate this value and this value for this type of x. Okay, it's the same calculation as over there. We had this linear combination going, right? So if you calculate this, you will see x transpose Lx over all x transpose x. This is for x and t. So this implies that this is equal to sum of Ci square lambda I divided by sum of Ci square. Same calculation as before. Okay, you take the big linear combination, you plug it into the quadratic form, you do all the reductions, and then you end up with this. Okay, but now the index is going from 1 to k. Okay, so this is less or equal to lambda k. Exactly, because lambda k is the biggest thing. It's less or equal to lambda k. Okay, so what we just argued is that this Rayleigh quotient on T is at most lambda k. So the max of that Rayleigh quotient is also at most lambda k. Okay? So if I took an arbitrary S prime, I cannot make the Rayleigh quotient go above lambda k. And in the other particular S prime, we achieved lambda k. So we're done. So max of the min is lambda k. Okay? So this is really, really useful fact. And there is a similar fact where you switch the min and the max. So it's min, max, and then also Rayleigh quotient. Should we write it? Okay, my watch says still a few more seconds, so let's write it. So the other expression, which is also equally useful, is that lambda k is also the min of the max. So you switch the max and min, Rayleigh quotient. And then this is x in S, not 0. And this is S in Rn. And now this time the dimension of S is just k. Okay, so these are two characterizations of the kth eigenvalue of any symmetric matrix, not just the Laplacian. But for the Laplacian we used, we didn't use anything special about the Laplacian really. Right? Okay, so this is that. So then in homework, there is this exercise that you can think about. So it's exercise number 5. So I want you to argue, this we won't do in class at all, but please try it. So argue that lambda 2 and lambda n are special. They have the number 5. In the exercises. It says lambda 2, you don't need this min-max. So lambda 2 is the min over all x that are perpendicular to the all ones of the Rayleigh quotient, or not 0. And lambda n is the max over all x's of x transpose Lx over x transpose x. Okay? So this is a corollary of Courant-Fischer. These two facts. And we're going to use this a lot. So it would be good if you can think about how to take this expression or that expression and just apply to lambda 2 and lambda n. And then you lose this double optimization. You just end up with one optimization, but you have to restrict the domain to be perpendicular to the all ones. Okay, that's the difference here. And here there's no restriction, but the max survives, here the min survives. Okay, so it's a direct application of Courant-Fischer. So maybe you can try this sometime. Maybe we'll use it already this afternoon, but think about this. Okay, all right, let's stop here. This is a good place to stop.